Okay. This way we get the silence on film. Okay, let's ease into it a little bit then. I hope that some people actually tried it. Doesn't matter if it works or not. Just, whatever it is that you came up with, what you were thinking about. So, um, let me do a real quick rewind. Okay, so in this class we're talking about databases. We've already talked about data structures and index files and algorithms. Right now we're talking about theory, where we're already past ER diagrams, which is a way to conceptualize uh, the relationships between the different entities that you're working with. And now we're working with relational algebra, which is a way to take relations that relational databases use, for example, and how to write queries. So the queries are taking a bunch of relations, applying some operations to different relations. Maybe you'll create some intermediary relations along the way, and you end up with one relation that is called the result of the query. We've talked about a few of these. For these examples, we're dealing with four relations that exist. Not every query needs every bit of the relation, or all of the relations, but whatever. So here, finding all restaurants frequented by at least one person. This is an example of a query. There's a set multiplication. I'm sorry. There's a cross multiplication that creates this intermediary large table. You delete rows from that table via the select, and then you return a single column with a project. So today I want to focus on this kind of query. And there's something about this query that's different than all of the other ones that we've seen. But I think that part of the best way to learn to appreciate these kinds of things is to try them for yourselves. So I'm curious, from last class, is there anybody who tried this? If not, I'll pick on somebody and um, go from there. Great. Yeah, sure. Let's hear it.
So I'm kind of definitely sure it's wrong.
Okay.
But
No problem.
I had because I had to multiply all four tables by each other,
Okay.
and then I renamed some of the columns which repeated in both tables. So do you want me to write it out?
Yeah, here, let me turn off my camera and can you read it and I'll write it?
Yeah. So person times renamed frequency,
Mm-hmm.
and frequency we rename name to name2.
Okay.
Times renamed eats, where name is equal to name3,
Okay.
times renamed serves, where restaurant is restaurant2 and food is food2.
Okay.
And then from that combination table, we select where name equals name2,
Mm-hmm.
name2 equals name3,
Okay.
and food equals food2, and restaurant equals restaurant too.
Okay.
And then we project name from that select.
Okay. So that's a select, and then that closes these project. Okay.
That's it. That's all I got.
That's it. Okay. Wonderful. Can you explain your thinking when you were putting this together?
Yeah, I could. So where it says find all the names of all the people, so that just said to me that table person has to be in the query or in this, and then who frequent only restaurants. If I don't know who is frequenting the restaurants, I wouldn't be able to figure out the name. So frequent table is there.
Mm-hmm.
Serving at least one food that they eat, so the eat table needs to be in there so that I could figure out um what is the food, how the final table rather is
Mm-hmm.
being narrowed down to find the person's name.
Mm-hmm.
And then serves just concatenates the restaurant and the food together so that also might be helpful. The renaming process is straightforward.
Yeah. Okay. Great. So let's see. Um, yeah. I guess because you're looking for people. Here you actually don't necessarily need the person table because I mean this isn't asking about ages or genders, and you know at least you have two tables that have names. But whatever. Okay. So what this query would do is this would find people who frequent restaurants serving at least one thing they eat. Whatever. Okay. Do you agree with this? Um, that's what this is doing?
I I think that's what it's. I hope that that's what it's doing.
Yeah, yeah. So this is what it's doing. It's finding people. So I mean, this whatever finding people. You're matching food, so that means that the food that they eat has to be somewhere a food that the restaurant serves. So that's the serving at least one thing they eat. And in addition to that, these are names of people who frequent these restaurants. So you can connect these through. Actually, um, this is sort of what you're doing. You're connecting. Well, person, if you like, as well. Whatever. Um, so you're connecting the names of the people here. That's this name, this name, this name. You're connecting the foods here, and you're connecting the restaurants here. So that's where these lines are coming from. Fine. Uh, So this is a query for people who frequent restaurants serving at least one thing they eat. But this is not quite this query. What's the difference between this one and this one?
It's the only restaurant serving at least one
Yeah.
food.
Mm-hmm. Yeah.
Right.
Yeah. So one way you might be able to proceed is that here you already have this, as a set. But there might be people who also frequent restaurants that serve things they don't like.
Right.
And so you'd have to remove that part. But okay, yeah, good. Yeah, so this is part of it. Yeah. Okay, cool. Thanks. Yeah, so this might be something you could build on, but this is going to be, I will argue, pushing a problem kind of down the road. Uh, yeah. So, did anybody else, when they were playing with trying to remove the cross multiply with the person table? Oh, I mean, it doesn't matter. It's just, I mean, it's not really doing much. Like, so what I mean by that is that the result of this query, as it's written, is the same as if you took out the person and you don't have to rename frequents. And I don't know, you do that to name 2, and then you don't need to check for this name 3. Like, the result of this query, those are two, the results will be the same of these queries. Yeah, because this table isn't really doing anything as far as finding people who frequent restaurants serving at least one thing they eat. So it's not wrong to have. It's just kind of redundant. Okay. Was there anybody who tried playing with this and found something about it to be difficult? Maybe, I mean, this is sort of the difficult part. Let me. Hmm. Okay. So I'm spending time on this because I believe that there's a systematic way to be able to formulate queries that deal with these situations. But I want to have you see what the situation is. Let me insert a table. Sounds rightish. I'll do a bunch of those. Okay. So here, let's say that we cross multiply the frequents, eats, and serves table. Then, sorry, just these. So I'm going to start making the sort of form of this. And I'm not going to go through the whole cross multiplication thing because, as you might know now, that can lead to a very, very long table with many, many rows. Okay, so this will be sort of the form of the table in here. When I say the table, I mean I'm getting rid of this, making this name 2, and getting rid of that. Okay, so the result of this 3 times cross multiplication will have a relation of this form. Now, the let's say from this relation, let's see how to say this. Let's say that here's John, who frequents, I don't know, McDonald's, name, I'm missing a column. Name, restaurant, name, food, restaurant, food price. Name, food, restaurant, food price. Sorry, I have to do this as quickly as I can. There we go, man. And then this should be also a food column. Okay, so one of these entries could be the text so it's actually readable. Okay, so one entry could be John, who frequents McDonald's, and he likes salad, and McDonald's serves salad for, I don't know, $3. And he also eats yogurt. And lo and behold, McDonald's also serves yogurt. And now you have some stuff here. I don't know, some other data. Well, whatever, I'll keep it here. Let's say that those are the only two things that John eats. And now, here's another entry. Hamburgers. So, $4. Okay. So whatever. I mean, you're going to get a really long table, right? Which is all of the different combinations. And you keep the ones where the names match. So, this row is talking about, the same John here who frequents this restaurant is the same John who eats salad. So that's the name part. The food. This food that somebody likes to eat is also served by some restaurant, and that the restaurant that this person frequents is also the name of the restaurant that serves this food. Whatever. Now, the problem is this. Find the names of the people who frequent only restaurants serving at least one thing they like. So maybe there's something how to say. Okay, let's say that John also frequents, I don't know, hot pot China, because John has friends who like really spicy food, and hot pot China serves a spicy hot pot for $15 because you share it. And right. So the problem with this is, let me turn on my camera. The problem with this is that SQL has no memory, or the select in SQL. That operation has no memory. So we've talked about all of the operations that exist. And so the cross multiplying, that's going to be creating this very large table. And then you want to select to go through and accept or delete rows. So when you see John here, we see that he does indeed, he hits all of the marks, right? I mean, in this row, the names match, the restaurants match, the foods match, fine. So we keep it and we move on. And each of these three rows check all the boxes, the names match, the restaurants match, the food matches. And so we keep these. This row we would get rid of because here the foods don't match. So and maybe if John frequents this place but he doesn't eat anything on their menu, because maybe he just goes with his friends. Like, I don't know, it's like across the street, and they'll go and he doesn't like anything there, but he likes hanging out. Whatever. KFC. Yeah. Yeah, or I don't know, like he's a who cares? So the thing is the select isn't able to go back and change its mind about, oh, wait a minute, hold on. I thought that John was a good possibility previously. Now that I'm seeing this, let me change my mind and go back up and delete these. That doesn't work. It doesn't work like that. The select, every single time it needs to be able to look at a single row, make a decision, keep it or throw it out, and move on. And it never revisits that decision. Okay? So that's why this word only is pulling a lot of weight here. Okay, so for quantitative reasoning, it's about truth statements, and queries are this is a truth statement about people. So here's a group of people, and for each one of them, I want to keep them if they frequent only restaurants serving at least one food they eat. That's a true or false statement. And for each if the statement applies to that person, I want to keep them. If it does not apply to that person, I want to get rid of them. Okay. Okay. So what I want to try to get across is how to break down true-false statements in a more careful way. Before I talked about this, for quantitative reasoning, this is an example of a lot of the vocabulary and the operations. So a predicate is just a sentence that's true or false. A predicate can be made up of smaller predicates that are called clauses. And clauses can be connected with operators. There's 3 operators: and, or, and not. So that's almost everything. In addition to these, there are, I'll put it here just so it's all one place. There's things called quantifiers. I don't know here. There's quantifiers. There's two of them, and only two. There's this backwards E, which means there exists. And then there's this symbol, an upside down A, that is for all. Okay, so those are all of the pieces. We have quantifiers, we have operators, clauses, and predicates. And these are the three types of operators. That's it. So a predicate is made up of clauses, operators, and quantifiers. Let me give an example of a statement that can be said to be true or false. Oh, I skipped something, but that's okay. All right. It rained for at least 1 hour last week. Okay, this is a statement that can either be true or it can be false. Making this more formal in logic, just using quantifiers and other predicates, this says that there exists a day last week where it rained for at least an hour. Sorry, there was a day last week where, sorry, let me change this a bit. It rained for an entire day last week. Then there exists a day last week where for all hours of the day it rained. Okay, now, so this is, I don't know, colloquial. This is formal, and this is formal with symbols, just so we can start getting used to it. There exists a day last week where for all hours it rained.
Professor, do you mind scrolling back up real quick to the where you wrote down what each quantifier meant? Yeah.
Yeah.
Perfect. Thank you.
Mm-hmm. Yeah, so the there exists looks like a backwards or a mirrored capital E, and the for all is an upside down capital A.
Professor, could you explain again how the first formal way that you mentioned the sentence is equal to the colloquial?
Oh, yeah. So, all right. So this can take a little bit of practice, but for statements that are true or false, you should be able to translate them into statements that only use predicates and quantifiers and these operators. Somehow, if a statement is, well, whatever, for a given statement, if it can be evaluated to be true or false, then there's a way that you can represent that statement using quantifiers and operators to come up with a predicate in this form. Okay. Okay.
I see. Okay.
So, for example, the colloquial thing of saying it rained for an entire day last week, you could be like a lawyer or something and say, okay, well, what you mean is that there exists a day last week where it rained for all hours of the day. Actually, I like it the other way, where for all hours of the day it rained. And so this, logically, is there's these parts to it. This must be true, that a day existed, and that this day, a day existed, and that also for every single hour of the day, it is true that it rained. If all of those things are true, then this statement is true. If there exists a day last week where for all hours it rained, then this is a true statement.
Got it. Thank you.
Yeah. Now, we also need to talk about what happens when you negate a statement. So that is to say, right now, this is true if this statement is true, then there exists a day last week where for all hours it rained. Now, if this statement is not true, if the thing that is actually true is the not of this statement, then we can distribute this not inside of the sentence. And the way that that works is that not there exists is the same as for all. And not for all means that there exists something. So, if there, trying to think of a quick, easy example. I don't know. Let's say somebody claims that there exists a black ball in a container. And if that statement is false, then that means that there does not exist a black ball in that container. Which also means that for all balls in the container, none of them are black. Negating a for all statement. If I say that all these balls in the container are white, if I'm wrong and that statement is not true, then that is to say that there exists a ball that's not white in the container. So this is why negating a quantifier turns it into the other quantifier. So with that, we could say that this statement, with the not applied to it, is that for all days last week, there exists an hour it did not rain. So if you have the statement that there exists a day last week where for all hours it rained, and that's a false statement, then the way to say the true statement would be that for all days last week, there was an hour where it didn't rain. Are people with me so far? Or am I starting to lose you?
Professor, I kind of understand it, but if we have time, could you write the examples that you gave about the balls in symbols?
Oh, sure. Sure. Hang on. Someone claims there exists a ball in a container that's black. If this is not true, then the truth is for all balls in the container, none are black. For all balls in the container, I'll say not black. So when we negate this, by the way, this isn't a 7. This is like if you drew a box and then you deleted the left side and the bottom. It's a 90-degree angle for not. So that is to say, if this is the claim, but it's not true, which means the thing that's not, the not of this statement should be true. And here we apply the not to the there exists, that turns it into a ball. And here, this is the part, a ball is black, is the part about this. I mean, like, the ball was black. But when you apply the not to it, it becomes not black. So for all balls in the container, no blacks. That would be the true thing if it's false to say that there exists a ball in the container that's black. Similarly, someone claims for all balls, color white. Color is white. Now, if this is not true, then the truth is, okay, so same thing, then that would mean that this is actually the true thing, which means that there exists a ball whose color not white. Okay, and I'm arguing that, like, now, knowing how to distribute a not through a statement or to come up with the complement of the statement, because that's what we're doing here. We're finding the complement of something. That's a useful thing to be able to do to formulate queries. Yeah, remember that, there's, with sets, if this is set A, then the complement of A is everything outside of it. So that's kind of what this is doing. It's taking a statement, or a predicate can only be true or false. There's no in betweens. Like, that's what quantitative reasoning is. Predicates are true or false. And so if this is a predicate, and you're saying that it's not true, then the truth is the not of this predicate. And so you can sort of rephrase it. Okay. And I'll tell you ahead of time, the reason why this is useful is because of exactly what we're doing here with this not statement. Relational algebra and SQL cannot deal with for-alls, as I tried to argue earlier, because there's no memory. You have to make a decision right now at every step, and you never have a chance to change your mind. So if you're asking, is this true for all things, it doesn't work. You can't do it. It just doesn't work. So, but what does work is seeing if something exists. So there exists are good for relational algebra and SQL. Anything that you can state as a there exists statement, you're okay. If there's a for all statement, you need to change it. And this is sort of a mechanism of how to do it. If you see a for all, you negate it. And that will turn the for all into a there exists. There's a little bit more to it than that, but that's what all of this is going towards. Taking a statement that sounds reasonable in English, okay, because this is most of the time if people ask you to make a query, they're gonna give it to you in this way. Like they're not going to be giving it in a lower level, helpful for you to make your SQL query kind of way. They're just going to say, I want to do this. And so from there, you can take a step back and try to put it in a way that'll be easier for you to deal with using quantifiers. And then you can, if there's any for all quantifiers there, then you can rearrange things. You can rephrase things to get rid of the for alls and to only have there exists. I'm realizing now I didn't talk about De Morgan's law. Is there anybody who remembers De Morgan's law? Has anybody heard of this? Or I would have thought you would have come up with this in your Python classes, maybe. Yes, okay. Do you remember what it was? Do you mind sharing? Not at all. Okay, no problem. Okay, so the way that I was just talking about how a not flips a quantifier, it would be nice to know how nots work on clauses. So, for example, for predicates P and Q, not P or Q. So first of all, this, P or Q. This, because these are predicates, they're either true or false, and so we'll say that 1 is true and 0 is false. So P or Q, it depends. I mean, if P is 1 and Q is 0, then this would evaluate to 1, because at least one of them is 1. If Q is 1 and P is 0, that's also 1, because that's the way that ORs work. Only in the case that P and Q both are 0 would this evaluate to 0. Okay, whatever. So these are predicates, and maybe we haven't evaluated them yet. If you wanted to say that not P or Q, this is figuring out how to distribute this not to each of these pieces. And the way that that distributes is, first of all, the not makes the P in the Q not P, not Q. For the or, it flips it to an and. So not P or Q is equivalent to not P and not Q. So that's one true thing. The second true thing is not P and Q is not P or not Q. So the same thing. I mean, if there's an and, it flips to an or, and then everything else gets knotted. That's De Morgan's law. Okay, let me go through this first with a truth table. I'll do it with one of them. I'll leave the other for an exercise for you. And then we'll use some common English to let you know that this isn't like nonsense. But, well, I don't know. Let's say here. Here. Okay, so we will go to the park if P, it's the weekend, and Q, it's sunny. So something will happen if something is true or false. If it's true that it's the weekend and sunny, then we'll go to the park. Now, if you not that, which is to say that you didn't go to the park, then that is either because it wasn't the weekend or it wasn't sunny. That's what De Morgan's law says. So it's fairly straightforward. I tend to think about it more of just its utility is how to distribute a knot. And it does the obvious thing for your P's and Q's, or for predicates, it just puts a knot in front of them, but for operators, it flips them. For time reasons, I'm going to skip the truth table here, if that's okay. But that's something, here, I'll sort of get you started if you wanted to do this. If you want to prove that these two are the same, then you just need to show that the truth table of one is equal to the truth table of the other. So these are all of the different values that P and Q can take in combination. Here you have P and Q. So, that's true if and only if all of them are true. You can do not P and Q, which is just the not of this column. So, all of the bits just get flipped. Okay, so there you go. That's not P and not Q. That's its truth table. Okay, how about, I'll just do it really quick. This, not P, not Q. Well, here, not P is just you flip the bits of P. So the first bit of P is 0, so that'll become a 1. Second bit is 0, so that'll become 1. I'm just taking these bits here, and I'm flipping them, because that's not P. Okay, that's this part. So then that would be 0, 0. Similarly, not Q. Now I'm going to flip the bits of this row. So that is 1, 0, 1, 0. And then we put the whole thing together, not P or not Q. So now we're doing the or of these. 1 or 1 is 1. 1 or 0 is 1. 0 or 1 is 1. 0 or 0 is 0. Okay, and there we go. They're the same thing. So these two truth tables are identical, which means that they're the same thing. Okay. Okay, so I really want to get through this query, at least as much as we can. All right. So the last thing I'm going to say about quantifiers is what I'm trying to convince you of is that this quantifier, the for all quantifier, is no good. In SQL, it's no good in relational algebra. But we can get, so these are bad. There exists is good. We can do a there exists. Yeah. Okay. So if these are bad, we can get rid of them because we can negate them. So if instead we can negate this, then we're in good territory. But the problem is that's now the negation of what the question was. So I'll just say something obvious. Not P equals P. Okay, so this is a way to apply the not operator to the predicate P, and basically P remains unchanged. If something is not true, then it's true. Same thing, if it's not false, then it's false. And so this is the trick we're going to be using. This not is going to result in a set difference. And this not is going to flip for alls to there exists. Okay, that's the way that this is going to shake out. Let me go to the example. And what? Oh, okay. Good. Just to give me a clean slate, I'm going to copy this first, and I'll give you the query. But why can't I do that? Stupid. So I'm going to the reason why I'm spending an entire lecture on this is because if you try to look in like a textbook or something, it will just give you the query, or it'll give you this statement, and it'll give you the query, and maybe you can understand the query, but where did it come from? Like, how did you get from this to that? And that is what I'm trying to give a way of doing. So here's the query. Very good. Okay, so this is it. Maybe there's other queries that could do it as well. In fact, there's certainly other queries that could do it, but this is a concise one. Concise, even though it's quite a bit going on there. And this has a couple of things that sort of jump out. I told you that we're going to be taking, something P. This is P. Okay. The names. Sorry. People who frequent at least one restaurant, only restaurants serving at least one thing they eat. So we keep the people for which P is true. But because it has this word only, and I'm going to talk about this is a for all. This means that for all the restaurants that serve this type of food, they go there. And in order to get rid of that, we're going to negate P, but we don't want the opposite query. We want the result of, what the query is asking. So we're going to negate it again. And here, this one is the set difference. And this, not P, is this. That is a there exists. Okay? Let me break down this query a little bit more. The way that, I think that this is maybe the way that most textbooks or things would present it. Here's this query, here's, what's this query? That's this query. Learn it, memorize it, I don't know. To me, this seems very mysterious, why it's this way. But let's first of all convince ourselves this query works. We'll kind of work our way from the inside out. This part of the query, actually, is there anybody who can tell me what does this do? Just this part. That should look familiar to other queries that we've seen in the past. Okay, how about coal? Got a mic?
Hey.
Hey.
So I guess in that cross product, it looks like you combine eats and serves,
Yep.
while also changing the food column, just renaming it to food too.
Mm-hmm. And the
Uh,
select and the project?
and would that be food has to equal food too?
Uh-huh.
Or is the food column would have to equal the food too for the select?
Yep.
And the other one, I'm not necessarily sure.
So what does it mean when the names match, or when the foods match, rather?
Does that mean all of the names in the food column have to match up with the names in the food too?
Yeah, right. So the food that this person eats is a food that the restaurant serves. Yeah.
Okay.
So that is. So this would return tuples of one column name, one column restaurant. So these are the names and the restaurants, such that the restaurant serves at least one food the person eats. Okay, so that's what this returns. A list of names and restaurants, such that for the people on that list and those restaurants, that restaurant serves at least one food that that person eats. Okay?
Okay.
All right, thanks, Cole. Oh, wait, hold on, Cole. Do you have any questions about that?
No.
Okay, so
No,
this part, yeah,
familiar
food
to me.
equals food too. That means that not only does the restaurant serve the food, but the person also eats the food.
Okay.
Why we equate those. Okay,
Okay.
great. All right, how about Jerry? You have a mic? Not seeing a mic, maybe no. Okay, how about Karnik?
Hey, can you hear me?
Yeah. Okay, so let's go out a little bit more and look at this part of the query. The purple thing that I'm highlighting. What would this
Okay.
return?
So since we already have the name and the restaurant of like the foods that serve like at least one person, right now we're taking the difference of hmm,
Let's move left to right here. What is
okay.
this? What's the frequents table? What is
That's
this?
that table just tells like what person frequents which restaurant.
Yeah. Okay,
So
and from that list, you're removing people or restaurant or the people who go to restaurants that serve at least one food they like. So what are you left with? You're taking frequents and you're taking part of it and deleting it. Like you don't want it. And so what are you left with?
so would we be left with like only one restaurant that one person frequents?
Not exactly. So let's see. These are people who frequent restaurants.
Okay.
And part of these people, are these people. So these are people who go to restaurants that serve at least one thing they eat. So who would this person be?
Uh,
I mean, and maybe
Oh,
there's many people.
would those be the people that so they'll be the people who frequent restaurants that don't serve what they want or what they eat?
Yeah. So this is the complement, right? I mean, or the not exactly the complement. Actually, it is the
So
complement.
it's kind of the opposite of what the blue box is stating.
Yes. Okay. This is okay. I'll have you explain this to me. People who only frequent restaurants serving nothing they eat. That's what this returns.
People Okay, so that so we're taking away so the purple is people who frequent restaurants serving nothing they eat, and we're
Yeah.
taking away uh people or restaurants who serve to people that have one food that they eat.
Yeah. Yeah. So we're taking people
Okay.
who frequent restaurants. We have a big, long list of people who frequent restaurants. From that list, we're going to take away the people that frequent restaurants that serve at least one thing that they like. So what remains are people who only frequent restaurants that serve things they don't like. It's a very strange group of people, but that's who they are.
So it gives us people who go to restaurants where they serve food that they don't like,
Yeah,
essentially. Okay.
exclusively food that they don't like. Yeah, yeah. It's not a normal group of people, okay? But
Okay.
this purple thing would find those people.
Okay, and it'll just give the names of the people or the restaurant
Yeah.
names as well.
Just the names, because we're just
Just the
projecting
name.
the name. Yeah.
Okay.
hmm Okay. Are you comfortable with that?
Okay. Uh, yeah, it's just that the statements threw me off. Like the
Yes.
compliment statement, it kind of threw me off. But I
Yeah.
understand it now with the circle diagrams.
Yeah. I mean, if you're a person who frequents restaurants, but you're not a person who goes to restaurants that serve at least one thing that you like, then the only things that are left are, uh, yeah, restaurants that serve nothing that you like, and you only go there. Yeah.
Okay. Yeah, that makes
Okay.
sense.
Yeah. So not a normal group of people, but them nonetheless. Okay. Thanks. How about Swathi?
Yes.
Hey. All right, now can you take us home? And what is this whole thing doing now?
So now it's I guess from where you left off, like the last part would be like the projection part. So it's like projecting all the names
Mm-hmm.
of, I guess, like what the problem says, like the people who only go like who go to the restaurants where they serve like at least one food that they eat.
Mm-hmm. Yeah, so again, let's go left to right. What is this?
So it's projecting the name of each person.
Yeah, so these are all people. Whatever. All the names of all people. Who cares? Names of all people. So here we have a big set. So this is all the people. And from that, we're going to remove the purple people. Um, Okay, and so same thing. What is this? What remains?
So it's just the names of all the people who, I guess, like it's like, so it's the names of all people, like without the people who frequently go to restaurants.
So they're all people except for these people.
Oh, so it's the people who don't frequently go to the restaurants. Wait, wait, people who only frequent. I'm kind of confused on how to like say it.
Yeah. Yeah, so you call everybody into the room with you. And then you say, okay, for people who only frequent restaurants that serve nothing that you like to eat, leave the room. And so then they file out. Now, who do you have remaining? These are people who, what?
They stay there because they have something that they like to eat.
Yeah. Or they're people who only frequent restaurants serving at least one thing that they like to eat. I mean, this is the query. That's the way to say it. These are people who only go to restaurants serving at least one thing they eat. So if you get rid of the people who only go to restaurants that serve only things that they don't like, then what remains are people who only go to restaurants that serve at least one thing they do like. I'm sorry, maybe this only people who frequent restaurants serving nothing they eat.
Professor,
Yes.
could you give a quick recap from the beginning, like very quickly, briefly?
Yeah, actually, so that's what I'm going to do now. And okay, yeah, actually, so I'll do this quickly, and then I'll review it and pick it up from here next time. Okay, here's the original query. Okay, find the names of all people who frequent only restaurants serving at least one food that they like to eat. This is, I think, the systematic way to go about it. You want to return people P such that for all restaurants X this person goes, there exists food Y such that P likes to eat Y and restaurant X serves Y. Okay? So this is just a more formal way of stating that these people, for all the restaurants that they go to, that if they only go to these types of restaurants, and that is to say that for all restaurants they go to, that's where the for all comes from, there exists a food that the person likes to eat and the restaurant serves that food. I want those people. Now, this has the for all, so I'm going to ask for not these people. Okay, so this logically should return the same set of people. Let me focus on the first not. This part. Now I'm going to take the not and I'm going to distribute it. Okay? So not for all restaurants X this person goes means that there exists a restaurant this person goes such that for all foods Y, either P doesn't like to eat Y or restaurant does not serve Y. Okay, so this, the people where for all foods, either the person doesn't like to eat it at this restaurant or the restaurant doesn't serve it. This is the purple thing. People who frequent restaurants serving nothing they eat. Okay, those are people who go to restaurants where all the foods that restaurant serves, either the person doesn't like it or the restaurant doesn't serve the things that they do like. And if the restaurant doesn't serve it, but they go there, then they're going to a place that serves nothing that they like to eat. Okay, so that's this, the purple part, okay? That's the part that flips the for all to a there exists, okay? This first not, okay? That's its job, is to do this. Now, this second not here, that is a set difference. Which is to say, return all people P except for these. Except for those guys. Whatever. Okay? And so here we're returning all people P except for these ones. Like we don't want those ones, but we want everybody else. Okay? So I don't know how exactly people would go from this type of statement to this type of query. This is the most systematic way that I can think of to come up with such queries. That's the, okay, hopefully that's the quick recap. I'll pick it up again from here next class. I'll hang around if there's any questions. When will I post this recording? Later today. Mm-hmm. No, I'm sorry, not yet. I'll try to ask them today. Actually, yeah, let me make a note of that. This has been like a horrendously busy week, but there's still some time today. Yeah, no problem.
Hi, Professor. Can you hear me?
Yeah.
Oops, sorry. I didn't know I was unmuted for like a little bit.
Oh, it's okay.
Yeah, I just wanted to go over my exam. I'm not like trying to get any points back because I realized from the work that I did and the one that I submitted the wrong one. But just for like some of them, even in the one that I submitted, I don't think that it was worth like a 20-point deduction.
Okay. Let me go through and I'll load up your exam and share the screen.
Sure. Thank
I
you.
think can I share it already? Yes, I should be able to. Mm-hmm.